Welcome back for experiment 5, where we're going to examine an elimination reaction and isolate the product through distillation. The goals of this experiment are to look at the elimination of a secondary alcohol and, following the isolation of the products through boiling, to analyze the outcome of the reaction and determine which product was formed as the major product. So the reaction we're going to be doing today will be starting with methyl cyclohexanol. We have two possible diastereomers, the cis, where the alcohol and methyl are on the same side, and the trans, where they're on opposite sides. Our starting material is purchased as a mixture, and whether or not the reactant is cis or trans should not largely affect the outcome of the reaction. We'll be starting by taking these and heating with phosphoric acid to afford an elimination. You could imagine two possible products forming. We'll look at the mechanism through which these can form on the following slide. One important consideration to note as we start this reaction is that the starting alcohol, which has this polar hydrogen bonding functional group, has a boiling point around 165 degrees. Whereas the products, which no longer contain the alcohol, have a much lower boiling point range from 104 to 109. Okay. We're going to take advantage of this boiling point difference to isolate the products from the starting material as they form. Okay, so let's take a look at the substrate. I'm just going to leave the stereochemistry out and draw the methyl cyclohexanol. And the first consideration we want to ask ourselves when considering the mechanism is, do we have a primary, secondary, or tertiary alcohol? So hopefully you've recognized it as a secondary. The next thing we want to do is evaluate the base that we have present in solution. So this reaction is actually catalyzed by phosphoric acid. And we can see that this is actually not basic at all. We certainly do not have a strong base in solution. The acid itself is also going to play an important role, as we saw during experiment 4, in allowing us to convert the alcohol, which is typically a poor leaving group, into a more favorable leaving group. So as we consider the need to improve the quality of the leaving group, our first step in the mechanism should be to use the phosphoric acid to protonate the OH group. As shown here. Now that we have a protonated secondary leaving group, it's possible to imagine the departure of the leaving group to afford a carbocation. So we have a secondary carbocation. Your head might be starting to wander to the possibility of carbocation rearrangements. I would encourage you, when this video is over, to draw out any other possible product formation pathways that you could imagine. So here we have the secondary carbocation, and I'm going to work with that directly. We have a proton on both of the neighboring carbons. So I'm going to label the one on the methylated position as HA. I'm going to label these protons as HB. Unlike the substitution reactions we did last week, you'll realize that when we use phosphoric acid, the conjugate base is not a good nucleophile. So we should not expect substitution products to come out of this reaction. Instead, now that we've formed a high energy reactive carbocation intermediate, we can see an E1 elimination mechanism by which this weak base will remove one of the available protons at the neighboring carbon to afford an elimination product. So I've drawn one possibility by abstracting HA. Alternatively, from the carbocation intermediate, we could have had the base choose HB at the less substituted carbon. And that would give us a different alkene isomer. So thinking about what you've seen in class, I encourage you to analyze these two products and these two pathways and decide whether you expect the deprotonation of A or B to be the dominant mechanistic pathway. Okay. In order to carry out this reaction, we're going to start with 5 grams of the cyclohexanol, and we're going to be heating it in the presence of 1.5 milliliters of concentrated phosphoric acid. As part of your pre-lab preparation, we're going to ask you to figure out how much of the elimination product you can possibly make. In order to do this, you'll need to figure out how many moles of cyclohexanol you're using. And that will tell you about how many moles of the alkene you can expect. And using the molecular weight, you can figure out how many grams. Now, of course, we do not know what ratio to expect for these two alkene products. That's why we're carrying out the experiment. But we know that they have the same molecular weight, so the overall yield of product is predictable. Let's talk a little bit about the distillation process that's going to be an important aspect of isolating our products this week. Distillation refers to the separation of a mixture by taking advantage of difference in boiling points. This is typically used when the components you are trying to separate are liquids. And unlike chromatography, it does not require a polarity difference between the molecules. And it does, however, require that what you're trying to separate has a substantial difference in boiling point. So if you think about what we said on the first slide, the starting material has a drastically different boiling point from our two products today. However, the two isomers that we're interested in studying have a very similar boiling point, only within 5 degrees of each other. And so we cannot expect them to separate using this technique. They may be isolated together. Okay. So how the distillation is going to work is you're going to have your reaction in a heating mantle, as we've been doing for the last couple of weeks, in a round bottom flask. In this instance, the flask is directly attached to a fractionating column. This column provides a surface area where, as the components of the solution start to vaporize, they will travel as vapor into this and slowly condense back down and vaporize back up and condense and revaporize. This allows an equilibration and a space for the lower boiling component of the mixture to reach the top of the fractionating column faster than the higher boiling component of the mixture. We place a thermometer at the top of the fractionating column with the tip shown as here, sort of at the entry point to an attached condenser. And this will allow us to measure the temperature of the vapor as it reaches this top part of the column. Okay. The thermometer is placed in a T-shaped adapter. And what this does is it allows the vapor, once it has saturated this thermometer head, to begin to travel over for collection. It's very difficult for us to collect and contain a gas. So once we have separated the molecules in the gas phase, we use a water-cooled condenser to condense that vapor back to the liquid form for collection. And this is the same condenser we've been using in our reflux apparatus. It's just positioned on a diagonal instead of the vertical as we're used to. We then have an elbow attachment here that has an opening to air. It's very important that when you're heating a system of volatile components, that you are not heating it as a closed system, which will result in an unfavorable explosion. And so we have an air outlet here that allows us to heat this system without building up a tremendous amount of pressure. And then you're going to have a receiving flask, and this is where you will be collecting the product that has come over as a vapor and condensed in the condenser. You can keep this receiving flask on ice to help make sure that it's cool enough and that it is cool enough to handle when the distillation is done. So this is just a recap of the distillation components that we're going to be using. You'll find all of this glassware inside of your hood, and probably the most interesting and difficult part of today's experiment is going to be assembling this for a solid apparatus with no leaks. You really want to make sure that at each of these connection points where, say, the fractionating column connects to the T-joint, or this T connects to your reflux condenser, that you have no openings. If you do, that can be a place where the vapor escapes the system and then we collect less product. Okay. So once you've achieved your distillation, these are some pointers to make the distillation go smoothly. You're going to have a product that ideally contains the alkene products. However, we carried out our acid catalyzed reaction with a large amount of phosphoric acid. And it's certainly possible that some of that acid has carried over with us to the product flask during the distillation. We're familiar from previous weeks with the notion that we like to put samples on the GCMS as clean as possible without residual salts and acids. So to remove this acid, you guessed it, we're going to carry out a separation in a separatory funnel, as we did last week. So you're going to empty the contents of your round bottom into a separatory funnel that you'll find in your hood, and you're going to add saturated sodium bicarbonate. Think about why we're adding bicarbonate. Also, try to think about which layer you expect to be the top and which you expect to be the bottom. Okay. You're going to wash with bicarbonate and water to isolate a clean organic layer. And just as we did in our first extraction, you're going to sop up any residual water by using the magnesium sulfate drying agent. For your organizational purposes, as you're reading through the lab manual, here's a pictorial representation of how the separation is going to work this week. I'm not going to walk you through every step since you've had experience here. The one difference between last week and this week is that once you've dried your organic layer with magnesium sulfate, you want to gravity filter into a pre-weighed vial. This will allow us to weigh the vial again after our product has filtered through and to obtain an isolated mass for calculation of percent yield. Okay. Once you have this product in your vial and you've weighed the vial, you're going to obtain an IR. Think about what this could tell you. If you had residual alcohol, what peaks might you expect to see in the IR? Think about the region between 2,800 and 3,000. If you have double bonds versus only sp3 carbons, where do you expect the signals for your CH stretching to show up? After obtaining an IR, you're going to prepare a sample for GCMS. And GCMS is going to be really important in distinguishing how much of each of the two isomers we drew on our mechanism slide we've obtained. Recall that we said these have boiling points of 109 for the more substituted alkene and 104 for the less substituted alkene. We said that given our distillation apparatus, we typically don't have great success separating mixtures that only have a 5-degree boiling point difference. So we would expect both of these products to have been isolated in our flask as they formed during the reaction. However, their boiling point difference is substantial enough that it should impact the way they elute from our GC column. Okay? So remember that retention time in the GC correlates to boiling point. Given this, which one do you expect to come out first and which one do you expect to come out second? You can use the corrected area of the first and second peaks to identify how much of each product was formed and validate whether or not your proposed product distribution was in fact correct. Lastly, you can use that mass to calculate a percent yield. So as part of the pre-lab, we asked you to figure out how many theoretical grams of alkene can you isolate from the reaction, given how much alcohol you're starting with. Okay. If you take your mass over the total expected theoretical mass, you can calculate a percent yield for this reaction. Okay. As usual, at the end of lab, all waste will be disposed in the waste bottles in your hood. So bicarbonate and residual phosphoric acid, anything from a graduated cylinder can be rinsed into the aqueous waste. And then you're going to clean and rinse all of your glassware thoroughly with water into the aqueous and then acetone into the organic. And we'll collect any filter papers and pipettes for solid waste. So that's the lab for this week. We're going to be exploring elimination, and we'll see you soon.